how do we combine quantum computing and functional programming, I think really gets to the core of that, because naively, I really can't, right? Because in functional programming, I'm trying to make sure that there's no global state, that I've explicitly tracked everything, and the actual types of inputs and outputs. And that kind of flies in the face of thinking about no cloning theorem, and I can't really copy state and things like that. But if you dig a little deeper, there's exactly the right tool in functional programming to help manage implicit global state that gets passed around and acted on: a monad. And so, like, kind of the approach that you tend to see to designing quantum languages is take that monad, the qubit monad of I accumulate what instructions I send to my quantum device and how I manipulate the state of that qubit, and make that first class in the language. So in Q sharp, the only global state that there is in a program is the qubits, and everything kind of implicitly acts by side effect on those qubits, but all the classical effects are explicit. So and that's very much so borrowed from thinking about functional programming ideas like monads. And you can see the history of that. There's a great blog post somebody on my team wrote, Alan Geller, about why we need Q sharp, that talks about kind of the predecessor languages like Liquid and how they were inspired by functional programming.
I also wanted to mention real quick, because I have gotten into this a little bit lately, but there's there's a thing in classical computing or classical computer science that's like formal verification, right? You've written a program and you want a tool to like verify that, and I guess it's commonly used in like, or basically the same task as theorem solvers. And there are some interesting approaches. I mean, these are mostly research based, but of using formal verification like as a tool to verify quantum programs. So like right now, you can do, unless the language stops you, you can do whatever you want with a qubit. That's kind of one of the nice things about using Q sharp, which is it knows you're going to talk to qubits, so it will only kind of allow an API that is physical. But if I'm just writing stuff arbitrarily in Python, well, Python isn't designed for quantum computers, and I can do things like copy variables and stuff like that, and it may not do what I think it's going to do. So, but yeah, I just think it's really cool that you can use some of these, really kind of more abstract computer science concepts like the monad and stuff like that in functional programming, and use some of those same tools to actually formally verify quantum programs as well, because again, they're instruction sets to a device. There isn't anything magically different about them really, other than the hardware.
There's kind of a long history of that, or rather of getting that wrong in quantum computing, that's really started to turn around recently. And that it used to be you couldn't pick up a single paper in quantum and like write down what that paper said, because there would be one typo somewhere, like a missing gate, and nobody ever ran the paper to see what it did, because you can't run a paper. So it's just, especially as we got started with things. Yeah, exactly. And I mean, in no case has a paper been like so terribly wrong that you can't get something, the algorithm just doesn't work even in principle. It's more like, when you're doing research, how do you make sure that you've actually implemented the algorithm correctly? And obviously simulating is one way to do that, but then that really hits limits as your computer gets larger and larger. So it's been really neat to see in the past few years projects like Quire and Squire and things like that use formal verification systems like Coke, so that a quantum program in those languages is the same as a proof that the program does what you intended to do.
I don't have too much experience with formal verification or theorem provers. Does a lot of this stuff boil down, like when you're thinking of things functionally, does this boil down to proving whether one function is equal to another function?
So that's not my area of expertise in particular, so please take with a grain of salt, but that's kind of my understanding, is basically that, and like making sure that you can express preconditions and postconditions in terms of functions, and show that the steps inside the body transform the tree to the post. Kesha Hialta, you know, has written some really neat papers on Jennifer Pagan. There's a lot of really cool research around that.
Mhm.
So what are the big exciting problems right now in the field?
This is the $1 million question that investors are putting their money down left and right.
What would we do with a quantum computer if it was everything we ever dreamed one would be? I think that's really the biggest open question for the field.
Mhm.
It's a question we have a lot of, directions on, a lot of progress toward, a lot of really good ideas, and a lot of work toward that. Like quantum chemistry is an example we highlighted in the book. There's a lot of chemistry libraries out there for quantum computing. So that's an especially promising direction. But, we've really not had the same depth of experience with applications of quantum computing we have with classical. So it's one of those where I think we're really just starting to see how many different ways it can be applied. And, there's a lot of neat work and, for instance, machine learning and things like that to see how can we use quantum computing there. So I think we're really starting to see that turn, but it's still somewhere where we have a lot to learn. And I think it's really neat to see new people come on board and bring new applications that they want to solve with them, because that's how we address that.
I was going to
Yeah.
say, what about cracking Bitcoin wallets?
Oh, goodness.
I'm dying on the inside right now, Paul.
Sorry.
No. I did at one point give a lightning talk called like quantum computing for the blockchain with machine learning. I just like smushed all of these together, and the lightning talk was like, no. That was it. No, I I will not comment directly on that one, which is I don't see any threat from that, basically.
Fair enough.
It's a much bigger question, as Chris said, of like, even if we magically had a quantum computer that was even arguably large enough to say run Shor's algorithm or something like that tomorrow, there is so much work between like everything from all the control electronics to make it to allow us to even like send those instructions to it, to how much of the rest of our classical computing stack, how do you if you had the device in the room, you can literally analog connect to it, great. How do you abstract that to like a remote sort of interface or an API? How do you abstract that to something you can access from the cloud?
Right.
Like there's so many other problems, and I think that's what's really I think, as kind of Chris was talking about, where a lot of the exciting developments are in the fields. Yeah, sorry, the dogs are barking outside. But I think that's really kind of what has drawn me from the hardware side more into the software side, that there's so much really cool stuff going on, and in particular with tools and experiences that people already know how to do. Like, what does DevOps for a quantum library or a quantum language look like? I don't know, but it sounds really cool, and I want to find out.
I mean, yeah, I think that's a really good one to call out, because like 6 years ago, as a postdoc working on quantum computing, what did I spend about 90% of my time on? Teaching people to use Git. I mean,
still,
I exaggerate for the sake of humor, but it's still one of those where you see a lot of the kind of software development practices. Because I swear, you take any physics program long enough and far enough, it will turn into a software development problem before you're done. And so then it's like you get all of these DevOps questions, you get version control questions, and how do you reproducibly deploy your simulation for a particular physics problem to your collaborators and to the readers of your paper. And so it's like, all right, well, let's throw it in a Docker container and use that to write our paper. And it's like, okay, roll back a few steps. What how did this turn into software engineering?
Totally.
but yeah, like I think that's one of the things, like actually one of the main motivations for writing this book was really to help make what, yes, we feel like we are reasonably well understand this, but we know that there are people with skills and expertise that we don't have. Like, I can say as a physicist, I think physicists are some of the worst coders that are in existence. Now that I've like kind of seen a little bit of like what a professional software development sort of environment and stuff looks like. Yes, I know no production code is perfect, but just like the fact that you could have CI and it's not just grad students sitting there hitting shift enter all the time. Like, so many things that we can use to improve, the iteration cycles here. And yeah, like there's just a lot of gatekeeping, I think, around either like at a subconscious level, like, oh, it's quantum, I could never understand that, it's so different, to like literal, you must have a degree or you must have learned math up to this point, to participate here. And literally, if you know Git, that's pretty much a good place to, and any other sorts of programming skills, that's a good start. Like, yeah, that's what I really like to do, is show people that this is actually an accessible thing, that they can have an impact on a really cool emerging new technology. Like, as Q Sharp is an open source language, almost all the other tool chains in the space, there's metaprogramming languages and stuff in Python. There's hardware interface packages and stuff like that for the literal pulse level controller devices, and they're almost all open source. So it's really cool. Like, you can get your name in papers working on these things coming entirely from a software dev side.
You, one of the biggest kind of software challenges going on at the moment is how to represent a compiled quantum program. And so like quantum intermediate representation, QIR, is something some of us get extremely excited about. But that's all built off of LOVM. So if you're an old hat at LOVM, that's a great place to jump into quantum and help out. So I mean, there's always these places where what is between us and where we want to be in quantum is a classical software engineering problem.
Yes, if you know LVM and are good at it, please get in contact and are interested in this. I'm not good at this. I'm but it is really, really interesting and very valuable when you're trying to deal with lots of these different packages and getting, because right now you got to do end-to-end conversions. Not fun. We need an IR like yesterday.
Well, this is a good call to action for anyone listening. Yeah. There's two good books to pick up to accelerate from classical programming, your classical programming career into your quantum programming career. Yeah.
Yeah, definitely. Where can folks find you online, Paul?
I usually give out my email address at the end of these things because I feel like if people have tolerated hearing my voice for an hour, then I don't mind if they reach out. So I'm orlandpm@gmail.com.
You can find myself and Chris mostly on Twitter because we're chronically internet damaged. So I'm crazy, the number 4, and then pi314. You'll see me in chat here too. And Chris, you're C Granade, right?
Mm-hmm. Also hang out on the Q Sharp community Discord, Sarah's stream Discord, and the Unitary Fund Discord. All 3 neat places to hang out for quantum computing.
Yeah, I haven't a lot recently, but I will be getting back to doing live streaming coding for quantum computers and stuff. So if you want to come, like, tell me where I've forgotten the semicolon or whatnot, or help me figure out what this error message is, please follow me here on Twitch, or all the stuff is on Twitter and stuff too. So, and check out our books.